Physics 2211, Lab 2, Projectile Motion. Lab purpose. The purpose of this lab is to observe and measure the position of the object that is thrown like a projectile. We then compare the motion of the projectile to a computational model that has no drag and drag. So we threw a paper ball and it moved with like a projectile as gravity was the only force enacting on it. So how did we do it? We filmed the video and imported it into Tracker, gathered the data from Tracker, created a computational model to model the path of the same object, added drag to the computational model, and compared the drag for each model. So eventually we had data for Tracker, we had data for the computational model, and we had data for the computational model with drag. We graph it all. So physics principles: average velocity formula, Newton's second law, velocity update formula, position update formula, all the concepts we use in lab 1, and then drag force, which is new. So Tracker video, we have a system, which is our ball, and our initial position 0.001, 6, and 0.18. And you can see we throw the ball from y equals 0.18, and it goes down, we throw it up, and it goes down, affected by gravity. You can see on the right the graphs of the x and the y position, who are linear and parabolic. Coding initial conditions, we have our mass, initial position from Tracker, velocity, initial velocity found from the average velocity formula, 0.03 for the time because 30 FPS, and then we have our gravity force, g is equal to 9.8 because that's the gravity constant on Earth, and then Fg, which is the vector for force of gravity, and then we have b, which is the constant for drag force. If you set this to 0, then we have no more drag force. If you set it to a higher number, then you have drag force. Calculation loop. So total time 0.4, that's how long it was in Tracker, and then we have drag force formula, which was negative b times the magnitude of ball velocity squared times v hat, and then we have force, the net force, which was the force of gravity plus the force of drag. Okay, so ball velocity, and then we use velocity update formula to find the position, velocity update formula, position update formula to find the position, just like we did in lab 1. Globe script results. So no drag. On the left we have no drag, and it went to about 0.7x, and then for the y, or for the one on the right, we have around 0.65. So you can see that on the left it went a farther y position than it did on the right. So comparing Tracker and computational data. Tracker and computational data, we have Tracker as blue, no drag as red, and drag as yellow. So one thing I want to talk about is, on hindsight, we should have thrown this paper ball with only an x trajectory, so only an x velocity. We threw it up a little bit with a y velocity, and that caused it to go up and then decelerate and then start accelerating again due to gravity. But because of this, our Tracker is the one where it is the highest. However, normally our computational data should have a higher graph than our Tracker. However, regardless of this, you can still see how the drag force causes the graph to all the positions to go backwards a little bit. So the drag force is a little bit, since the drag force is up, the y position, final x and y positions are going to be lower. So error, Tracker difficulty, it was hard to see the frames, and throwing with y velocity, that was what I was just talking about, how we threw it up a little bit. If I was to do it again, just throw it completely horizontal, that way gravity can start doing its thing, and it'll start accelerating down eventually instead of having to accelerate up and then accelerate back down. So, and also the paper ball had uneven shape. This affects the drag. So what does this mean? Do any of our models predict the terminal velocity? No. This is because if my object had reached terminal velocity, the velocity would have flattened out, but it didn't. It's obviously, there's a slope. And an experiment that we could design is dropping the object off a much greater building, like something really tall, and giving it more time to reach terminal velocity. So what if? What if I threw the object straight up with the initial speed? It would take longer for the ball to reach the ground, obviously. I did not mess this up, or I did mess this up, because I kind of did this, but if we were to throw it horizontal, it would have reached the ground faster, because it doesn't have to go up, decelerate, and go back down, and accelerate again. So yeah.